This video is on using the area under a graph. Let's just talk about an example here first before we talk about the graph and the area. So suppose you travel at 50 miles per hour. For 4 hours. How far did you go? All right, so how far did you go from your starting point? Now this is something that you probably do all the time on your own if you're just driving in a car, right? What we usually do is we say the distance equals the rate multiplied by the time, right? So distance equals rate times time. Our rate in this case is the 50 miles per hour times the time you traveled for, which is 4 hours. And 50 miles per hour times 4 hours tells you went 200 miles, right? So you're 200 miles from wherever you started. Now suppose that instead of me giving you the question like this, I actually told you that we knew the velocity function v of t was equal to 50 miles per hour. Right, so I'm telling you that up front. That's the same thing as me saying you're traveling for 50 miles per hour. It's constant, right? So the velocity is remaining constant, v of t equals 50 miles per hour. If I was to sketch a graph of this, here's our t-axis or our x-axis, but this will be in hours. And this axis here will be your y-axis, which is v of t. It's your velocity in miles per hour. Well, this is the same as like saying the line y equals 50. Right, so we got a t-axis, which represents hours, and then we got a v of t axis, which is our y-axis. And then if I want v of t equals 50 miles per hour, we said that's like the same as saying y equals 50. That's a horizontal line through 50. So it's going to look like this. This is the line v of t equals 50. It actually goes on forever in both directions. Keeping in mind, though, that since t is time, we're not going to use anything to the left of 0. And now, suppose I said, how far did you travel over the first 4 hours? Well, if I had the time as 4 hours, so, we start at 0, 1, 2, 3, 4, right, what I'm really going to look at is, let's look at this area under the function there. And this area is going to be equal to length times width, right? If I was looking for this area of this rectangle. So the area is equal to length times width. Well, what's the length? Well, the length here, right, this is 50 miles per hour times the width, which is 4, and that equals 200. Now, keeping in mind what the units were on this, right? So the 50 was in miles per hour times the 4, which was in hours. So what are the units on the 200? Well, the hours cancel, and it's 200 miles. So what that shows us is that the area under the curve, right, will give you the total distance traveled, right, or the total displacement. So what this shows us is that this 200 miles is the same as that 200 miles we said right there. So the area under the velocity curve gives us the distance traveled. And that's going to be important as we get into future sections. In this case, it was pretty easy to calculate that area because the function was a constant. Now, to find the position, right, so to find the position, we want to use the antiderivative. All right, so to find the position given velocity, we use the antiderivative. And the reason we would do that is that we remember velocity is the derivative of position, so the antiderivative of velocity will give us position. So we use the antiderivative. And we'll make that a little neater. So we use the antiderivative. So if I knew that v of t, which I just mentioned above, so v of t equals 50, right? And that's in miles per hour. If I wanted to find the position function, remember we called that s of t, that's equal to the integral, right, of v of t dt, the antiderivative. And then taking the antiderivative here, this will be equal to the integral of v of t, we said was 50, so the antiderivative of 50 dt. While evaluating this, the antiderivative of a constant, remember, is just that constant times the variable with respect to, so 50t, and then plus c. So this would be the position function, right, s of t. So we really have that s of t is equal to 50t plus c. And I can write that down here just so we have it. Now, suppose I said, we started at, a starting point where, so we start at position 0. So s of 0 equals 0. So at time 0, we're at position 0. We haven't gone anywhere yet. I can use this to help me find c, right? So substituting into this, s of 0 would equal 50 times 0 plus c. And what's that supposed to equal? It's supposed to equal 0, right? So s of 0, 0 is the t value. And then I set it equal to the y value, which is also 0. So 50 times 0 is 0, so we got c equals 0. So if c equals 0, then s of t is just equal to 50t plus c, which is 50t plus 0, so it's just s of t equals 50t. So if I asked you what is s of 4, it's saying what is the position at a time of 4 hours? Well, we would substitute in, s of 4 equals 50 times 4, and that equals 200. Remember, the units on this is position, so this goes back to being miles. So, in this example, we're showing how the position relates to the antiderivative of velocity. It also shows you how the area under the curve gives you that same value, right? So the area of under the curve and the antiderivative are actually closely related. And we're going to talk about this more in the next section than this section, but it's just to show you, looking ahead, that is how these are related to one another. For the next example, we'll look at a specific function and then how to determine the area under the curve for that function. So we're looking at this here. Say this example. The function below is the marginal cost per suit when X suits are produced by a company. And they'll give you the function, we'll say it's C prime of X. Remember, marginal cost is the derivative of cost, so C prime of X equals 0.0008 X squared minus 0.45 X plus 100. And it's defined on, I'm going to give you an interval from 0 to 400. And the directions here are going to say to estimate the area under the curve using 4 rectangles. So let's make sure we talk about this first before we actually go through and pursue what we're going to do. First off, C prime of x, that's the marginal cost, derivative of cost. They've limited our interval from 0 to 400 for x, that's our domain. It says estimate the area under the curve using 4 rectangles. In the previous example we saw when we were talking about the velocity function, because it was constant, it was very easy to use geometry to find the area. Here, the equation for C prime of x is actually quadratic, right? This x squared is going to be a parabola. So it's not as easy to use geometry because you know, these don't come out to exact geometric shapes when you're looking at the area under the curve. Later on in the next section, we'll talk about how to use antiderivatives to find that. But here, when we estimate the area under the curve using the 4 rectangles, what we're really doing is we're going to be finding the cost for the first 0 to 400 suits that are produced. So let's take a look at what this looks like in terms of a picture, and then we'll actually pursue the finding the area under the curve. So first off, let's draw in, this is a sketch now, right? Here's x, here's y, which when I say y, this is actually, in this case, C prime of x, right? So we have x, we have C prime of x. X is going to be the number of suits. Y, which is C prime of x, is going to be, maybe let's leave it as C prime of x, is going to be dollars per suit, right? That's the units on this. C prime, right, the derivative is the units of C, which is dollars, per the units of x, which is suits. And we know we have this function that's a parabola. All right, I'm not going to be completely exact on the shape of it, but I'm going to draw it in here as a rough sketch. You know, we're going to have a y-intercept, we know, of 100, so we know it's going to start here at 100. And we know that it's a parabola, and the parabola itself is going to look something like this. All right, so this is going to be C prime of x equals 0.0008 x squared minus 0.45x plus 100, and that's the function. Now, when we do this, we're going to talk about using 4 rectangles. Now remember, this is from 0 to 400, so the x value here is 0. The x value on the opposite end of what I'm looking at is going to be 400. And so this is really the interval I'm looking from 0 to 400. When it says to use 4 rectangles, what that's really telling me to do is that's going to give you a value what we're going to call n, being the number of rectangles. So the 4 rectangles tells us n equals 4. But it also gives us a way of deciding how we're going to split up this 0 to 400, because we're going to call this delta x, meaning the change in x. And it's going to be equal to what they call b minus a over n. Now that's kind of a weird way to say it, but what I'm really saying is that when you look up at our interval, it goes from a to b. So our interval goes from a to b. So when I say b minus a over n, what I'm really saying is take 400 over 0 and divide it by the number of rectangles you need, and that'll tell you how to line up your axes, right? Your scale on your axes. So this will equal 400 minus 0 over n, which is 4 rectangles, and this ends up being 400 divided by 4, which equals 100. So what that's telling you is that on my axes, right, I'm going to split this up going from 0 to 100 and then all the way up to 400 by 100. So, you know, you would have, here's 100, here's 200, here's 300, and then you already have 400. So that's how I'm coming up with the scale for my axes. What you're really seeing here is this distance is the delta x. It's the b minus a over n, and that's the same for all of these, right? It should be equal. And now what we're going to do is it says to use 4 rectangles to find the area. So just as a quick note, and this is the way your textbook does it too, we will use left endpoints to find the area. There are other ways of finding the area. You could use left endpoints, you could use right endpoints, you could use the midpoint, there's trapezoid rule, there's a bunch of different rules that we could use. Because we're just learning it here, we're going to use left endpoints, and I'll show you what happens if you were to use right endpoints. So let's talk about if I was to use left endpoints on what this graph actually would look like. So when I say left endpoints, what I'm really saying is I'm going to draw on these rectangles and I'm going to use the function here. So left endpoints means I'm starting here for my left side of my rectangle at 0, and then I'll use 100, 200, and 300 as the left endpoints. That's what I mean when I say left endpoints. So let's talk about what would happen. All right, I'm going to call this LHS for left-hand sum. You may have seen this before, but in case you haven't, we're going to find the left-hand sum. And I'm going to come up with this through a formula, but I want to make sure we see it. So, you know, the x value at 0, right, has a y value which is c prime of 0. And we're going to take this and we're going to draw our rectangle in from our left endpoint. So we're using our function, the y value at 0, because we're using the left-hand side. We're starting at 0. We're going to come to here, and then we're going to go down to 100. And I want to find the area of this rectangle. Well, the area of this rectangle, and I'll write it generally so you can see it. Right, the height of the rectangle is 100, but really it's c prime of 0. We know that's 100 there. But to keep it general, this would be c prime of 0 times the width of the rectangle, which we know is delta x, which we know is 100. Now, for now, I'm just going to write it like c prime of 0 times delta x, so you can see where it's coming from in this shape. And then what you want to do is you want to add on the next rectangle. Remember, we're going to use 4 rectangles. That's what they told us to use. So this is my next endpoint. So I'm going to go up to where my function is, which is right here. Right? And what's this going to do? It's going to go over and then back down. All right, so we're making these rectangles. So you're going to go to 90-degree angles from where your function is and then back down. And you've got another rectangle. So the second rectangle, what's the height on that? Well, the height on this is whatever the height of the function is, the y value at 100. So it's c prime of 100. We'll evaluate what that is in a minute using the function times the width. The width, again, is delta x. In our case, it'll be 100, but just so you can see it generally. Plus the next rectangle. Okay, this is the left endpoint. So we go up to our function, then we go over to the right, and then come back down. Well, what's the height of this rectangle? Well, it's the y value of c prime of 200. So it's c prime of 200 times the width of this rectangle is delta x, plus the last one here. You got this 300 is your left endpoint. We go up to the function, and then we go at a right angle over, and then back down. And so you would have the height of this rectangle is c prime of 300 times the width of it, which is delta x. Now we'll be specific about this, and when you do it on your own, it might be easier just to substitute in the values, but I want to make sure you can see where all of this is coming from. So when I look at this here, I've got 1, 2, 3, 4 pieces I'm adding together, which is the 4 rectangles, and that's important. You should have an understanding of where that's coming from. Now when we do this, right, you could factor out the delta x from all of this and then multiply it in. We're going to do some calculations for c prime, and then we're going to, evaluate these. So when I look at this, the c prime of 0, right, we know what that is already. C prime of 0, the y value there is 100. If you were to sub x equals 0 in here, you get 100 out. So it's 100 times delta x, the width. Well, the width we know delta x is 100, plus c prime of 100. And you can substitute this into your calculator. 0.008, make sure you got 3 zeros, 0.0008 times, we have 100, because we're doing this sum here, so 100 squared minus 0.45 times, subbing in for x, 100 plus 100, this equals, what do you get, 63. So this will be 63, right? All we're doing is substituting into our c prime formula with 100, so 63 times delta x, which is 100, plus, and we can continue to substitute in like this. Now to save time, I will just tell you what these are. C prime of 200, if you sub 200 into your function, the height there, right, the y value that you get from there is 42 times delta x, which is times 100, plus c prime of 300, right? This is the y value here. It's the height. When you substitute into here, you will get 37 times 100. And so we want to add this up. So we're going to have this 100 times 100 is 10,000 plus 6,300 here plus 4,200 plus 3,700. Just adding these together now, we get that this is equal to, and it's 10,000 plus 6,300 plus 4,200 plus 3,700. Adding those up, you should get, this is $24,200. Remember what we're finding. If this is C prime, right, that's the marginal cost. When we find the area under the curve, we're getting the antiderivative when they sell 400 suits. So it's going to be $24,200 is the estimated cost for selling well, I shouldn't say for selling, I should say for producing. All right, so $24,200, adding these up, is the estimated cost for producing 400 suits. Now it's an estimation, and the reason it's an estimation, if you look back up here, right, is that some of these rectangles go above the curve, some of these rectangles go below the curve. So it's not going to be exactly whatever the antiderivative, whatever C of x would be through the first 400 suits they produced. It's really just going to be an estimation based on these rectangles. This part's going to be an overestimate, this will be an overestimate, this looks like an underestimate, this looks like an underestimate. So it's not going to be exact. In a similar way, you could use right-hand endpoints. If I was to use right-hand endpoints on this, right, for a right-hand sum, maybe I'll do this on the next page. For the right-hand sum, you would have RHS for right-hand sum. The way you're going to do this, it's the same idea, except for, remember our intervals from 0 to 100, 100, 200, 200, 300, 300, 400. My first interval will start over on the right-hand side. So from 0 to 100, I'm actually going to go up to the function here, where it hits there, and then I'm going to go backwards to make the rectangle. So you're going back to the previous endpoint, because that's how you're going to get your first one for a right-hand sum, because this is the base, this is the right-hand side. You go up to the y value there and go over, and that's going to be your rectangle. So this rectangle here is now what I'm taking the area of, and the area of that rectangle would be, what's the height of it? The height of this one is C prime of 100. All right, times the width. The width is still delta x, so we would have C prime of 100 times delta x plus the next rectangle. Remember, we're doing right endpoints, so I started with this one, so I'm going to go over here to 200. I go up to my function, so I'm following this up here, and then I'm going to go backwards from there at a right angle, and this will be my next rectangle. Well, that rectangle there, what's the area? Well, the height is C prime of 200 times the width of this is delta x. It's going to be 100 in this case, but times delta x, just to try to keep it general. Plus the next rectangle, using the right endpoint, I would go over to 300. That's my next endpoint. I'm going up and then following that over. Remember, you're making a right angle and then back down. So we've taken the area of that rectangle. The area of this, the height is C prime of 300 times the width of it, which is delta x, plus the last rectangle. You're going to the 400, you're following this up to your function, so we're going way up here now, and then we go back at a right angle and then down to make our last rectangle. That last rectangle has a height of C prime of 400 times a width of, well, the width is still delta x. Now when you do this, we're using 4 rectangles. When it says use 4 rectangles, you should have 4 terms in your sum, which we do, right? 1, 2, 3, 4. And you shouldn't be adding on the other endpoint. And you can notice the difference between the left-hand sum formula and the right-hand sum formula is that the middle parts, right, are going to carry over. It's just the ends are different, right? This one had the c prime of 400 delta x. This one had the c prime of 0 delta x. And it's because of which endpoint we're using. But there should be only 4 terms in your sum. So when we go to calculate this, we already calculated most of these. C prime of 100, right, we already have. C prime of 200 we already have. C prime of 300 we already have. So C prime of 100, well, that was, we had 63 times delta x, so times 100 is our delta x, the width, plus the next rectangle, C prime of 200, we evaluated that to be 42 times delta x, which is 100. Remember how you're getting these. You're subbing into the C prime function to get that value. Plus C prime of 300, we just did that a minute ago. We have 37 times delta x, which is 100. Plus C prime of 400, we haven't done yet. If you want to, you can type that into your calculator. You could go back to the previous function and just sub in 400 instead of the 100. All right, so times 0.45 times 400. We're just replacing all the x's here with 400 in that original function. And we end up with, I've got 48. So this will be 48 times delta x, which is 100. All right, so you can do these calculations for C prime on your own, but have an understanding of what they are. They're the heights of those rectangles. So now we evaluate 63 times 100 is 6,300 plus 4,200 plus 3,700 plus 4,800. And when you add those up, 6300 plus 4,200 plus 37 plus 48, we get 19,000. Now remember what you're finding here. If this curve is C prime of x, right, the area under the curve from 0 to 400 gives you the cost for producing the first 400 suits, right? So C prime is the marginal cost. When you find the area under the curve, you're finding the cost for that amount of suits. So this is $19,000 is the estimated cost to produce 400 suits. Now, we found this here using right endpoints. We found this here, right, 24,200 using the left endpoints. You know, which one's correct? Well, neither of them are correct, right? This 24,200 is based off of these blue rectangles, right? The right-hand sum, the 19,000, was based off of these black rectangles. And the truth is that the actual cost is somewhere in between, right? Because we have pieces that are either underestimating or overestimating depending on where they are in terms of the curve, either below the curve or above the curve. But the point being is that you can generally do an approximation here using rectangles. A lot of what you'll see in our textbook uses left-hand sums. In other textbooks, it might use right-hand sums. And then they might tell you to use either or. There could be midpoint formula, which is another way of doing this, which, you know, changes a little bit what you would do, but not that much. And then there's also, you know, trapezoid rule and Simpson's rule, things that you might learn in other courses. But for now, this is just to give you the general knowledge. So I'm going to write this as in general, just so you can kind of see this. So I get it with a specific example, but this would be just the general form. So in general, to approximate the area under the curve over some interval from A to B, right? So those are just the endpoints, using n rectangles. Now, you have to remember that in our example, A to B was 0 to 400, n was the number of rectangles they told us to use was 4. That's why we had 4 values in our sum when we were adding it together, 4 terms. You know, if you were asked to use more rectangles, that can happen, and that's okay. If you are using more rectangles, the delta x would get smaller. That b minus a over n would shrink because you're going to actually be using more rectangles over the same interval. So the width of the rectangles would be smaller. So let me draw this as a sketch just so you can kind of see it. So suppose we had this function, which I'll write here, and we'll call this f of x. You know, this is the x-axis and this is the y-axis. And let's say that we start at some value a to some value b, right? That's the interval. And I'm trying to approximate this area under the curve. Well, what we do first is we say, okay, we want delta x to equal, right, because we're going to try and figure out how we split this up. It's equal to b minus a, right, the endpoint. It's b minus a divided by n. The number of rectangles tell you how to divide up where these values are going to be for your scale. Now, this is a. I'm going to call this x sub 0. That's just another way of labeling that same point. And then I'm going to say, you know, next point would be x1. The next one is x2. We're just defining this generally because we don't know what these values are. And this will continue on until you get to x sub n minus 1. And I'm going to call b x sub n. So a certain number of these endpoints are in here. But understanding that, you know, these are going to be numbers when you do it on your own. Delta x gives you the width of each rectangle. So the space here between, you know, x0 and x1 is delta x, whatever that number comes out to be. All right, the space between x1 and x2 is delta x. Between x2 and x3 would be delta x, all the way up to the very end. The spacing between them is always delta x. Then to find the total area, right, using the left-hand sum, what you would really do is you would, remember, start on your left endpoint, and you're going to go up and then right angle over and then down. And you want the area of that rectangle. Well, the total area is going to be approximately, we'll use a squiggly equal sign for approximately. It's f of x0 times the width, which is delta x. And then you would add on the next rectangle. So you'd start at x1 and you'd go up to your curve and then over and then down. And then how do you find the area of that? Well, it's f of x1 gives you the y value, it gives you the height. Right, the y value there is f of x1, right, times this width, which is times delta x, plus you could keep going like this, right? For the next one, you would go up from x2, you would hit here, and then come back down. Well, what's the width? The width is going to be delta x. What's the height? Well, the height is f of x2, so it's f of x2 times delta x, plus you could continue like this all the way through, right? Because remember, this we don't know how many there are. This is just generally speaking. Your last endpoint you would use is this left endpoint. So you would come to here, go over, and then back down, right angle. And when you do that, the last one would have a height, so plus f of x sub n minus 1, which is just the height here at whatever this value is. Right, that's the y value, times the width. The width is still delta x. And you would add those up. So this is using, right, when I just did this, this was all using left-hand sum. So how do I write this? Well, this is actually going to be equal to, all right, using the left-hand sum here. You can factor out the delta x from each of these. So that's the first thing to think about. And we use summation notation. We call this a Riemann sum when we do this. And I'm going to say, you know, I'm going to use these little subscripts. I'm going to call them I. And the first one's equal to 0. And how far did I go? I went up to n minus 1. So it's from I equals 0 to n minus 1. Well, these are all, generally speaking, f of x sub I times delta x. So what I'm saying is each of these terms, this means sum means add them up. This is a summation notation. So this means take the sum, and you're adding up all of the rectangles that have this area. So f of x sub 0 times delta x is saying take the first one. Then this says iterate this up 1. So then f of x sub 1 times delta x means you add the second one. Then iterate this up 1 again, so you're at 2. So f of x sub 2 times delta x. And you're adding these up. So this is just a shorthand way to write this. Remember, this is the left-hand sum. If I write it like this, this is called a Riemann sum, just generally speaking, when you have that summation notation. So this is called a Riemann sum, and you're adding them all up, all the way up until n minus 1 is your last subscript. All right, because you're using left endpoints. If you were approximating using right endpoints, right, the right-hand sum is very similar. Just remember, you're going to start over at x sub 1. So you would write this as a sum from I equals 1 to how far do you go? Well, the last endpoint's a right endpoint, which is where b was, which we called x sub n. So from I equals 1 to n. And still this part stays the same, of f of x sub I times delta x. Just means that you're going to start here at this term and you'd be adding these all up, and then you'd add one more that includes f of x sub n times delta x to get the last rectangle you'd get from working backwards from the right endpoint. So, you know, these formulas are good to know, generally how I wrote them, but what's more important is being able to reproduce what we did in that example with the marginal cost, because you're really not going to use this notation when you write it. You're really going to write it more like how I did here when I was taking the left-hand sum and I was being very specific about the function and what the values were. I didn't use a condensed notation here, and I probably wouldn't when I go to solve these, but this is really just showing you the general setup of how you would find them. So hopefully this gave you an idea of how area under the curve works. You know, when we have a derivative function, right, and I take the area under the curve, it's really giving me the antiderivative over that, that interval. So that's why when we had marginal cost, right, it gave us cost. When I had those first examples where I was talking about velocity, it gave us how far our position changed, right? So that's what we did with the earlier examples. So hopefully this helps, and in the next section we'll look at how the antiderivative can be calculated exactly rather than using approximations.